Welcome to the Deep Dive. Today we're jumping into something truly fascinating, the search for planets beyond our own solar system.
Yeah, exoplanets. It's gone from pure speculation centuries ago to this incredibly active field of discovery now.
Exactly. And I think, like us, probably everyone listening has looked up at the stars and wondered, are we alone?
Yeah.
So this deep dive is really about exploring how we've started trying to answer that huge question.
And we're using a great source for this, Perryman-Gaia-0n9.pdf. It gives a really solid overview of the history, the methods, and just the sheer number of exoplanets we found.
Right. So our mission today is basically to unpack the main ways we actually find these planets. We want to give you a clear picture of how these techniques develop, some of the surprising twists along the way, and maybe look ahead a bit too.
Sounds good. Where should we start? It feels like we've known about exoplanets forever now, but that wasn't always the case.
No, definitely not. So where did the idea first come from?
Well, interestingly, the core idea of spotting a planet when it passes in front of its star, the transit method that actually goes way back, 1851, Dionysius Lardner mentioned it.
1851, wow. But he wasn't thinking specifically about exoplanets, was he? More about why some stars seem to flicker.
Exactly. He was suggesting it could explain some periodic variable stars. Applying it to finding planets around other stars, well, that was the next step. And it came with huge challenges.
I can imagine, like just the odds of it happening.
Yeah, think about it. For a planet like Earth, taking a year to orbit, a transit is rare. You'd have to stare at that one star for ages just to see it happen maybe once or twice.
And it has to line up perfectly, right? The orbit needs to be edge-on from our perspective. It's like trying to see a gnat fly across a searchlight miles away.
Precisely. And then there's the dimming itself. It's incredibly tiny. David Beloriski, back in 1938, he calculated you'd need photometry measuring brightness with a precision of 0.01 magnitudes.
0.01. That sounds tiny. Like, what does that even mean in practical terms?
It means detecting a minuscule drop in light. Really, really difficult with the technology they had back then. The theory was there, but actually doing it, that was another story.
Okay, so transits were tricky. But then there was Otto Struve in 1952, right?
Yeah.
He had this wild idea about planets orbiting really, really fast, like in a day.
Yeah, that was wild, especially when Mercury, our fastest planet, takes 88 days. It seems totally counterintuitive based on our solar system.
So why did he suggest that? Did he have any evidence?
The source doesn't really detail his reasoning, but his intuition was, well, uncanny. Because the first major exoplanet found around a sun-like star in 1995, 51 Peg B.
Let me guess.
It had an orbit of just 4 days. Not quite 1 day, but incredibly short compared to what we knew. Struve was decades ahead of the curve. It really shows how theoretical ideas can sometimes leap ahead of observation.
That's amazing. So the clues were kind of there, or at least the ideas were, long before we actually found anything.
And even before the first transiting planet was confirmed, that was HD 209458b in 1999, people were already pretty optimistic about the transit method for finding big planets, like Jupiter's, and even thinking about Earth-sized ones eventually.
And, well, it definitely paid off, didn't it? The transit method just exploded in the last 20 years or so. Ground-based surveys did work, but the space telescopes, CROT, Kepler, TESS-SE, they seem to have been the real game changers. Why space?
Oh, space is key. Getting above Earth's atmosphere gets rid of all the blurring and twinkling. You get much clearer, more stable measurements of star brightness.
Right, makes sense.
And the numbers show it. As of February 2021, transits accounted for something like 3,300 out of the 4,300 or so known exoplanets. Kepler, especially, operating from 2009 to 2018, was just a planet-finding machine. It stared at one patch of sky constantly.
3,300, that's incredible, just from watching stars dim slightly.
Huh?
But it's not the only way, is it? What about radial velocity?
That's right, radial velocity, or the Doppler shift method. That had bagged, 824 planets by that same date, Feb 2021.
Okay, so how does that one work? No dimming involved?
Nope. This one looks for the star itself moving. A planet orbiting a star doesn't just circle it, they both orbit a common center of mass. So the star actually wobbles back and forth, just a tiny bit.
Because the planet's gravity is tugging on it.
Exactly. And we can detect that wobble by looking at the star's light. As the star moves towards us, its light waves get slightly compressed, shifted to the blue end of the spectrum. When it moves away, they stretch out, shifted to the red. It's the Doppler effect, like with sound waves.
As the star does a little dance, and we see the rhythm and its light color changes. That's pretty clever. Okay, what else is in the toolkit? Microlensing. That sounds complex.
It is more complex and relies on chance alignments. Gravitational microlensing found about 106 planets by early 2021. It uses Einstein's idea that gravity bends light.
Okay.
So if a star, maybe with a planet, passes directly between us and a much more distant background star, the foreground star's gravity acts like a lens, magnifying the light from the background star.
Like a cosmic magnifying glass.
Exactly. And if that foreground star has a planet, the planet's own gravity adds a little extra blip to that magnification signal. It's a very specific, temporary brightening pattern. It takes patience and a bit of luck to catch one.
Wow.
Hmm.
Using gravity itself as a detection tool. Okay.
Yeah.
Transit, radial velocity, microlensing. The source also mentions astrometry. But it says that only found one massive planet by 2021. Why so few compared to the others?
Yeah, astrometry has had a challenging history. The basic idea is simple enough, though. It's related to the radial velocity wobble. If a star is wobbling back and forth towards and away from us, it's also wobbling slightly side to side across the sky.
Okay, that makes sense. So you just track the star's position super accurately.
That's the idea.
All
Try to measure that tiny side-to-side motion against the background stars. But tiny is the key word here, and super accurately is the challenge. From Earth through our wobbly atmosphere, measuring that minuscule angular shift for a distant star. It's incredibly difficult, like trying to spot a flea jumping on a dog from a mile away.
Okay, yeah, I can see how that would be tough. And the source calls its history checkered. Sounds like there were some bumps in the road.
Oh, definitely. What's interesting is that people recognized astrometry's potential very early on, around the same time Lardner was talking transits, mid-19th century. In 1855, Captain W.S. Jacob actually claimed he'd found a planet around the star 70 Ophiuchi using astrometry.
Who did? So was that the first exoplanet discovery?
Well, no. Unfortunately, it turned out to be incorrect. His measurements or interpretation didn't hold up under scrutiny later on.
Ah. And that wasn't the only time this happened with astrometry, was it?
Not at all. Thomas C. made claims in the 1890s. Eric Holmberg thought he saw planets around Proxima Centauri and 70 Ophi, again in the late 30s, early 40s. Karja Strand reported a Jupiter-mass planet around 61 Cygni in 1943.
All wrong.
All later shown to be likely due to instrumental effects, systematic errors in the measurements, or maybe just wishful thinking pushing the limits of noisy data. They were right at the edge of what was possible, maybe even beyond it.
It must have been frustrating.
Immensely. And probably the most famous case was Peter Van de Kamp. He spent decades, starting in the 1960s, arguing for planets around Barnard's star based on tiny wobbles he measured on photographic plates. Huge debate for years.
Yeah.
Also eventually disproven by more modern, more precise measurements. It seems the apparent wobble was likely due to subtle adjustments and changes in the telescope optics over the years.
Wow. So a lot of false starts. It really highlights how hard science can be, especially when you're working at the absolute limit of your tools.
Absolutely. But, even these false claims are important. They showed just how difficult astrometry was, and they pushed astronomers to think about better instruments and techniques. They didn't find planets, but they helped define the problem.
And the ultimate solution seemed to be get off the Earth, go to space.
Exactly, get above the atmosphere. Paul Coteau and Jean-Claude Pecker were talking about space astrometry for planet searches way back in 1964.
So the idea was there quite early.
And the first big step in that direction was the Hipparcos satellite, launched by ESA in 1989.
Was it designed to find planets?
Not primarily, no. Its main job was to measure the positions, distances, and motions of stars with unprecedented accuracy for astrophysics generally. But Wilhelm Gleis suggested using its data to look for Jupiter-like companions later on.
And did they?
Well, after the first radial velocity planets were discovered in '95, astronomers went back to the Hipparcos data. They couldn't confirm those specific planets with astrometry. The wobbles were too small or the orbits too long for Hipparcos, but they could use the data to put upper limits on the planets' masses, which was still valuable information.
Okay, so Hipparcos was a stepping stone, which leads us to Gaia.
Precisely. Gaia is essentially the successor to Hipparcos, but on a vastly more ambitious scale. The ideas started forming around the time of Hipparcos, with people like Eric Hugg and Lennart Lindegren developing concepts.
More ambitious how?
Well, Hipparcos measured about 120,000 stars. Gaia was designed to measure around 1 billion stars.
1 billion. Okay, that's just staggering.
It is. Measure their precise positions, distances, motions, and their brightness and colors, and even radial velocities for millions of them. It was a massive undertaking proposed to ESA and adopted in 2000. Lennart Lindegren and I were heavily involved in shaping the science case.
1 billion stars.
Yeah.
The data processing alone must be incredible. And you mentioned the science case did finding exoplanets feature prominently.
Oh, yes. Out of the huge proposal document, there were 5 pages specifically dedicated to exoplanet detection via astrometry. We knew it had huge potential.
So even back in 2000, you could see this coming.
We could see the potential, yeah. I actually worked with a young researcher then, Anna Colorado, to make some early predictions. We looked at the expected number of stars Gaia would observe within about 200 parsecs. That's roughly 650 light years.
Okay.
Combine that with estimates we had at the time for how common Jupiter-like planets might be, and factored in Gaia's expected measurement precision.
And what did you come up with?
Our initial ballpark figures were somewhere between maybe 10,000 and 50,000 detectable Jupiter-like planets.
10,000 to 50,000. That's an enormous number.
It was definitely exciting. Of course, those were early estimates. I was ESA's project scientist for Gaia through its development. And launching something that complex always takes time. We hoped for 2012, but it actually launched in 2013. Building Gaia was a huge challenge.
I can only imagine. So as the mission got closer to launch and the instruments were better understood, did those estimates change?
They did, yes. They became more refined. People developed much more sophisticated simulations of how the instruments would perform, how the sky scanning would work, used updated planet occurrence rates from early discoveries, and built better models for pulling the planet signals out of the data.
Right, getting more realistic.
So, for example, simulations by Casertano and colleagues in 2005 predicted Gaia might find around 8,000 giant planets, say 1 to 3 times Jupiter's mass around stars, similar to the Sun.
Still a huge number.
Definitely. And then later work, like ours published in 2014 just before launch, looked at a wider range of stars and distances. That suggested Gaia could find perhaps 21,000 Jupiter-mass planets with long orbits out to 500 parsecs in its first 5 years.
21,000.
And potentially up to 70,000 if the mission lasts for 10 years, which it looks like it will.
70,000 potential detections. It's incredible.
Yeah.
But it's important to note, right, these are mostly Jupiter-like planets in Jupiter-like orbits, not necessarily Earth's in the habitable zone.
That's a really crucial point, yes. Gaia's strength is in finding massive planets in wider orbits, the kind that cause a larger, slower wobble that builds up over the mission's lifetime. It's less sensitive to smaller planets in close-in orbits.
So we'll be finding Earth 2.0 directly, maybe?
Probably not in large numbers, no. But finding these Jupiters is incredibly important scientifically. They tell us a lot about how planetary systems are structured.
How so?
Well, in our own solar system, Jupiter plays a big role gravitationally. Having a giant planet out there might affect how inner rocky planets form and evolve. So finding systems with Jupiter analogs could tell us which systems might, architecturally speaking, be more similar to our own. They're like indicators or maybe gravitational sentinels guarding the inner system.
Gravitational sentinels, I like that. So finding these Jupiters helps us understand the context for potentially habitable worlds, even if Gaia doesn't find those worlds itself.
Exactly. It gives us the bigger picture of system architecture. And there's another bonus. Gaia is expected to find some transiting planets too.
Oh.
Just by chance, some of the stars it monitors very precisely for astrometry will also happen to host planets that transit. The estimates are maybe 25 to 50 transiting planets with periods of 2 or 3 years.
And why are those particularly interesting?
Because they'd be relatively long-period transiting planets compared to many found by Kepler or TESS. And because Gaia gives us such precise information about the star, they would be absolutely prime targets for follow-up observations with other telescopes, like the James Webb Space Telescope, to study their atmospheres in detail.
So Gaia finds them, and then other telescopes can zoom in. That makes sense, the different methods working together.
It's all about synergy. Which brings us back to that quote from Gene Schneider the source mentions. He said that while transits are dominant now,
astrometry with Gaia may prove to be the most powerful in just a few years from now.
Yeah, that really feels like astrometry's journey coming full circle after that difficult history.
It really does. After all the struggles and false starts, space-based astrometry with Gaia is finally unlocking the potential that astronomers dreamed of over a century ago. It's a testament to sheer perseverance, wouldn't you say? Absolutely. So wrapping this up, we've gone from Lardner's early musings on transits in the 1850s, through the tough early days and some surprisingly accurate guesses like Struve's, to the boom times of transit surveys like Kepler and the cleverness of radial velocity and microlensing.
And finally, the long-awaited rise of high-precision astrometry with Hipparcos, and now, especially, Gaia. It's been quite a ride.
It really has. We've gone from wondering if other planets existed to having catalogs of thousands found by these incredibly ingenious methods.
And Gaia is poised to add potentially tens of thousands more, primarily these large Jupiter-like worlds in wider orbits.
Which leads to a final thought, maybe. If Gaia potentially finds, say, 20,000 or even 70,000 of these Jupiter analogs, what does that sheer number tell us about how common different types of solar system architectures are out there? Does finding so many systems with giant outer planets increase the odds that some of them also have smaller rocky planets further in, maybe even in the right place for liquid water?
That's the million-dollar question, isn't it? Or maybe the billion-star question now.
Right. It makes you wonder about the sheer variety the universe holds, and whether systems like ours, with that kind of sentinel Jupiter, are common or rare. Something to think about. Thanks for joining us for this deep dive.